Hello, chemistry students. Today in our video lesson, we are actually looking at Standard 1A, where we are evaluating the merits and limitations of the different atomic models in relationship to the size, charge, and position of the protons, neutrons, and electrons. We have 5 atomic models that we will look at briefly, and we're focusing just on the models. If you're wanting some extra information about the experimentation that led to the models, and how the scientists got there, feel free to look at some of the additional resources that have been shared in Google Classroom. So our first atomic model that we will talk about is actually called Dalton's atomic model. As part of our opener activity, I have y'all reviewing an infographic and just telling me about any patterns and things that you see. I would hope that somebody has noticed or mentioned that the models maybe get more complex or have more information as we go from 1803 to 1926, which is our current model. Hopefully somebody's noticed that a lot of the models have a positively charged portion and a lot of them have a negatively charged portion. Interesting thing to note is that our knowledge of the atom really only started about 220 some odd years ago, not 2000, 220 some odd years ago. So a lot of our knowledge in chemistry is fairly current, especially when you compare it to stuff in some of the other branches of science. So looking at our first atomic model, this is John Dalton. And in the early 1800s, Dalton actually came up with the first atomic model. His model was analogous to a billiard ball. So if you've never played billiards, it's also called pool, but it's basically just a solid sphere. Dalton's model, Dalton at his time thought that you could not get any smaller than the atom, so he just thought the atom was a solid ball of stuff. He even used specific symbols to represent different elements, and he was able to show some interesting things with his model. He was able to show how the elements were made of tiny particles, and that the elements of one atom, or the atoms of one element, are identical, but different elements are different from each other. So each element has its own unique mass. He also was able to show how these elements combine to form different compounds, and that those compounds interact with each other to do chemical reactions. So the reactions is just the arrangement of those particles or those atoms. Now, for being the first atomic model, he wasn't too bad. I mean, he did pretty good considering the limitations that we had in the early 1800s. But there were some major flaws. There were some major drawbacks to Dalton's model. And first and foremost was that he felt the atom was as small as you could get. Back in Dalton's time, they had not yet discovered the electron or the proton or the neutron. So he thought that there wasn't anything smaller inside that atom. Now, we now know that there are neutrons and protons in that nucleus, and that their electrons are outside the nucleus. But at Dalton's time, he thought, hey, you couldn't get any smaller than that. Also, another flaw with Dalton's model was that he couldn't account for light given off by elements or by metals. He couldn't account for particles or charged ions. And in his time frame, they knew that those things existed and they knew that they occurred, but his model could not explain those observations. So those are some major limitations to his model. In terms of position, Dalton doesn't have a nucleus, protons, or neutrons, or electrons. His is just picture a solid basketball, soccer ball, just a solid sphere. So if I were to summarize Dalton's model, it's called the billiard ball model or Dalton's model. It did account for the different masses and different sizes and elements being particles, but it thought you couldn't get any smaller, and it didn't have an internal structure. So major drawbacks for it. So fast forward almost 100 years, late 1800s, early 1900, John Jameson Thomson, J.J. Thomson, created what was then called the plum pudding model. It was our second atomic model, and there were several that came out in very quick succession, and this happened to be one that many people liked the most because they could visualize it, because plum pudding was a very, very popular dessert. Not that anybody really knows what plum pudding is nowadays. picture kind of analogous to like oatmeal or oatmeal with raisins in it. That's kind of about the best you can get. So our plums were the negative electrons, and the pudding had a positive charge. So I figured most everybody's at least seen watermelon. Even if you don't eat it, you at least can visualize what it looks like. So if I were to take his plum pudding model and kind of relate it to a watermelon, he had the positive piece would be the watermelon meat, that red part of the melon, and my negative electrons are the little seeds that are inside the watermelon. So we could pick the seeds out, we can move the seeds around, but we really can't do much to the red piece. It just had a solid red charge. Now, it's interesting, and if you're kind of curious to see how Thomson's model relates to TVs and the cathode ray tube, check out some of the supplemental videos. It's kind of interesting how he determined that there was a negative thing in the model. So his model added electrons. It also did have some internal structure. He said that we had this positive goo and we had negative electrons. And he was actually able to use his model to illustrate how electricity was generated, how light is given off. And he could have different masses with his model. You know, a little scoop of pudding for hydrogen, big scoop of pudding for like lead, even a bigger scoop of pudding for like uranium. But his model had some limitations. So, major flaw in Thomson's model is that it didn't have empty space. In his model, that atom was filled with positive pudding. It also couldn't explain how things could have a charge. Again, they knew that things had charges. They were able to detect and interact with ions, but his model couldn't explain it. Sorry. So, not as big of a fast forward, like 5, 10 years. Okay, 7 years. I can't do math. Rutherford came along. Ernest Rutherford. His model is called the nuclear model. And he did some really interesting experiment with alpha particles and gold foil. And what he realized was that if Thomson model was correct, then the particles should do like it shows on the image for part B. They should just flow straight through. But what Rutherford actually detected in his experiment was that most of the particles did fly right through, but there were quite a few particles who were repelled back to the detector, and even others who were just deflected just a little bit, so they didn't actually go straight through. That led Rutherford to determine that there's something in the center, that there is a positive dense center. So Rutherford was actually the one who coined the term nucleus. And he said that that nucleus had a very dense mass and a positive charge. He also said that the electrons orbited outside the nucleus. So like each electron had its own path around the nucleus. So a lot of the nucleus was empty space. Now, Rutherford's model, as I said, is also called the nuclear model. And what his model said was that the atom had a tiny positive dense center. So he knew that there were protons in that center. We call it now the nucleus. That center basically has all the mass of the atom. And that the center, the nucleus, was positively charged. Now, what Rutherford was able to determine was that in most elements, the positive charge is balanced out by the negative charges of the electrons. So if I had a positive 3 nucleus, I had 3 negative electrons to have an overall neutral atom. But now that we were able to specify charges, he could actually explain about the ions and how ions were formed. Rutherford's model was also the first model to have empty space, and he stated that those electrons moved around in that empty space outside the nucleus. Now, to me, looking at that illustration of Rutherford's model, to me, it kind of sort of looks like a Jimmy Neutron graphic. I don't know if you guys ever seen that cartoon, but it is still a 2-dimensional illustration of Rutherford's model. Well, now in, 2022, we've got computer graphics and computer generated images. So we can take Rutherford's two-dimensional model and turn it into a 3D model. So this is kind of a 3D illustration of what Rutherford's model would have looked like had he had the computer capabilities that we have now. And it shows in the center that nucleus with a lot of empty space. And each one of those little zoomy lines is an electron. And the electrons are moving around outside that atom in kind of semi-predictable paths. Now, 2 dimensions, 3 dimensions, you can kind of see some slight differences. Not only that, but you can actually see in the computer graphic that the electrons are moving, that they're not stuck and stagnant in one place. So Rutherford's model, if we were to look at it in terms of kind of a summary, it again is called the nuclear model. It had empty space. This was the first one to have empty space. It was able to explain ions. It had an internal structure. But Rutherford's model had 2 major flaws. First and foremost, and I don't know why I don't have it first, but first and foremost is stability. In terms of the mathematics of Rutherford's model, based on his layout, the electrons would lose energy as they orbit around that nuclei. And as they lose energy, their radius would decrease, and eventually they would smack into the nucleus. This implies that the atom's not stable. And we know, and he knew at the time, that atoms are very, very stable. The vast majority of them are extremely stable. But his model could not account for that stability. Another thing that his model couldn't do is it couldn't explain why individual atoms produce discrete line spectra. We will actually see examples of this later in the course when we look at our flame test and our atomic emission spectrums. But basically, he couldn't explain why individual elements gave different colors and different lines. He could explain how they were given off light, but not why they weren't all the same. So after Rutherford, just a couple of years later, a student of Rutherford, Niels Bohr, came up with his own atomic model. And he really only made one major improvement to Rutherford's model. All he did was he added energy levels. He added orbitals and stated that the electrons move in specific energy levels around the nucleus. Now, he was able to use this to actually explain better how that light was given off and how we were able to get specific line spectra from certain elements. He experimented specifically with hydrogen, and his model works perfectly with hydrogen. Many people call it the planetary model. And with that planetary model, you've got the center of the nucleus, which at his time they thought only contained protons. We now show Bohr's model with protons and neutrons, but at his time, it was just positive things. And then he shows the electrons outside that nucleus. So there is a predictable pattern with Bohr's model and how the electrons go. That first energy level, you have 2 electrons. Second energy level is 8 electrons. Third energy level is 18 electrons. And there's actually a mathematical expression that would allow you to calculate how many electrons would be in the outer energy level for any energy level. And that's 2n squared. So you've probably seen these drawings before. These are the ones that you probably did in physical science. But let's say I wanted to do a drawing and I wanted to look at the 5th energy level and how many electrons maximum that 5th energy level could hold. Well, 5 squared is 25. 25 times 2 equals 50. So my 5th energy level holds a maximum of 50 electrons. Now, Bohr's model, if I'm looking at a stagnant version, you can kind of see an illustration of what it looks like on the right. Again, it's not a great representation in terms of size. The nucleus and the electrons, that's not a great illustration to show how much smaller the electrons are when compared to a nucleus. But Bohr's model does give us that internal structure. It does give us the different masses, and it tells us about the empty space. He's able to explain the light given off. So if you look at this graphic at the bottom of the screen, we can see energy coming in. And when that little line comes in, my electron jumps up to a different energy level. And then after a while, it loses that energy. That's the little squiggle going away. And the electron falls back down. So he was actually able to explain this with his model. He could explain the ions and was able to show excited state. But his model only worked for hydrogen. Only really works for hydrogen. Now, stagnant two-dimensional images can only show so much. And I just hit the wrong button, so please don't. Oh, snap. Okay. Ha ha. Sorry. Sometimes me and my technology don't get along. So this is an animated version of Bohr's model. Still really looks like it's 2 dimensions. And Bohr knew that atoms were 3-dimensional. So I wouldn't think that this would be the most best representation of it. But it does actually show how he visualized the electrons moving around within specific orbits. So Bohr's model was probably the last one that you learned about in physical science, but it is not our current atomic model. In fact, our current atomic model shows the atom as the electrons living in a cloud and the protons and the neutrons in the center of the nucleus. Now, by the mid-1920s, we had already detected that nucleus. It didn't happen until, I don't remember the exact year. It didn't happen until, I think, the early 20s, that Chadwick actually determined that there was a neutral thing inside the atom. So at Schrodinger's time, they knew about the protons, they knew about electrons, and they knew about neutrons. But what Schrodinger did was he said that electrons don't travel in a path. They do exist in different energy levels, but they don't have predictable paths. In fact, he said that it's not possible for us to determine the path and the speed that an electron is traveling at the same time. It's kind of interesting to note that Schrodinger has this very complex mathematical calculation, and he was able to develop his model based on wave calculations. And what his model shows is the probability of where we're likely to find an electron. So quantum mechanical model is our current model. And basically it says that our matter has both properties of particles and waves. Those waves particles are what gives us the cloud, that element electrons cloud. And those clouds have various shapes. We will see a little bit later in this course as we go into more detail about the quantum mechanical model, what these shapes look like. But it's very fuzzy illustration of what an element should be. So one illustration can show the quantum mechanical model with that positive nucleus with your neutrons in the center, and the cloud has little dots. Each dot does not represent an electron. It represents the probability of where an electron can be. So depending on the element and the number of electrons that are in there, you could have some elements with electrons in that first energy level. So this little orange circle. You could have electrons in a second energy level, which is represented by that blue circle. Or with a larger element, you can actually see electrons in both the first energy level, second, and third. But each one of those little dots represents the probability of where we're likely to find electrons. And what his wave equation did was it told us where in this cloud, so this is one model for Schrodinger's quantum mechanical model, where in the cloud we are likely to find the electron based on where the element lives on the table. Now, different ways to visualize the same thing, but our quantum mechanical model is called, the cloud model. When we say that the electrons live in the cloud, that's what we actually mean. But it still has some limitations. If I'm looking at it on a piece of paper, it looks like circles and flowers and graphs. You don't actually get the 3-dimensional representation. Not only that, but it's really hard to show how big the atom is in compared to the size of the nucleus, and how small the electron is in compared to the size of the nucleus. So our current models do have some limitations. So on the right side, you see the different wave functions that are generated by the equation that we saw on the previous slide. And this tells us what shapes that our electrons are likely to form. And there are different ways that people have visualized these shapes. So I'm going to show a short little clip of a song. That was not what I wanted.
Signaling each other with genetic. Electrons move too much. Slow down your pace and put that orbit on me. Come on now, follow my lead. Come on now, follow my lead.
Ah, dang it, didn't stop fast enough. So notice here, they're trying to show the electron probability as that blue cloud or that pink cloud. And that nucleus is that center plus sign. So each squiggle represents where an electron could be. Ultimately, what it came down to is we end up representing them with arrows. So one electron is shown as one arrow, but that one electron could be anywhere in those clouds.
Come on now, follow my lead. Let's take a shape they do. It's the states of the quantum goes through. And when the one approaches to combine and recording.
So in terms of models, we can actually use this quantum mechanical model to show how elements form bonds and how these big complex molecules are actually able to interact with each other and use this three-dimensional shape to predict what molecules are going to look like before we've ever actually seen them. And in terms of like medicines and drugs and stuff like that, this is really, really important because it allows us to predict a thing's function before it is ever actually synthesized. So our quantum mechanical model, like I said, it does have some limitations, and I kind of want to show you some illustrations that, that will show you what I mean by size. So a couple of examples here in terms of mass. So I don't know if you realize this, but the electron basically is massless. It's 1,000 times smaller than a proton or a neutron. It is 100,000 times smaller than your average nucleus. So if I were to have a penny be representation of an electron, a bowling ball would represent an average nucleus. Okay, well, let's don't look at an average nucleus. Let's look at specific examples. So I've actually got two here. I've got hydrogen and I've got gold. So in terms of hydrogen, picture a golf ball. So a golf ball, it's about 1.7 inches. That golf ball is the nucleus. Well, in hydrogen, hydrogen only has one electron. Its electron, if the nucleus is the size of a golf ball, its electron's almost a mile away. It's actually 0.8 mile away, but again, visual representation, almost a mile away is that one little electron. And it's a dot in comparison to the size of the golf ball. So one other example is my gold atom. Gold atom has considerably more protons and neutrons than hydrogen. It has considerably more electrons. So let's say my gold atom is a foot. So the radius is a foot. So the whole atom is about yay big. Well, the outermost electron in gold, if this is my gold nucleus, that outer electron is 3 miles down the road. 3.3 miles down the road is the last electron in gold. Give you an idea of how big the space is between the two and how small an electron is when comparison to other stuff. So these are two great little graphics kind of summarizing all of the atomic models. We didn't really talk about Democritus because he doesn't have a true model, but you see the other 5 here. Again, with our Schrodinger model, our cloud model, each of those little dots is trying to represent an electron's probability, and that nucleus in that particular one's not shown very well. That one actually shows the nucleus much better with that positive charge, but to me it does a worse job of showing the electrons because it's kind of fuzzy and you're not realizing that it's a probability map. So that is it for atomic models. If you've got questions, definitely make certain to ask. There is a supplemental video that I have included in here that goes into a little bit more detail about some of the background for how these scientists created these models. But for our standards, we are looking at the limitations and the merits of these 5 major models.